Riemann zone. And then, if you want to turn it into a real, okay, first of all, is this ever exact?
No.
It is.
If you get
small enough. What makes it exact?
Delta as it gets closer.
When you do the limit. Yeah. When you do the limit. So you're going to start approximating, and then you're going to say in the next thing, in the next frame, if I take the limit of my Riemann sum, if I take the limit of my sum, and you guys probably took most of those notes. If you take the limit of that, it actually becomes exactly the value, right? That's the integral, okay? So that's your, I mean, these are related, so you could put this in one or put them in two different, I don't know how you're going to relate it. You're going to tell the story. And then, we start with fundamental theorem of calculus number 2. And then we come back here to FDC2. Now, what is FDC2 going to say?
How you evaluate an integral.
Right, so FDC2 says we're going to find, we're going to come up with a method for finding, FDC2 says the area under the curve is equal to the displacement of the antiderivative, right? So that's FDC2. So you'll have your two functions, and the area under here is equal to the displacement here. That is very ugly. Okay? Now, I'm doing my mock-out. You can do whatever you want. And I'm just going to have it. I want to make sure you have the flow correctly. Does everybody understand what I mean by this, even though it's very ugly?
Wait, what?
What am I saying in it? It's very ugly.
Area.
The area under the curve. So this is going to be your f, and this is your f prime, right? So I did it backwards. This is your original function. If you want to find the area under this function, you have to take its antiderivative, and you get the displacement. The area under the function is the displacement of the antiderivative, right? Correct? I'm saying if I said it really quick, like 2 weeks ago, you'd say, "What are you talking about?" Hopefully that makes sense. So you're going to explain this logic, but then you're going to say, "How are we going to figure out?" The question is, how do we figure out the area under the curve? Okay, we want to know what the area under the curve represents, but how do you calculate the area of the curve? And one method is you could use simple geometry. Okay, so you have simple geometry, so you would do, we did our simple, yeah, let's do the two axis. If you remember, we did the simple analogy. If I'm driving 70 miles an hour, if I'm driving 70 miles an hour for 6 hours, then I'm going to go 420 miles, right? Okay? I'm using the wrong color. So you guys, I assume we have all that in your notes, right? Okay, and then you came down here and you went across. Now we're in the derivative function. This is f prime, and this is 70, and this is 6, right? Why is the height 70? Remember that?
Because the slope is
because the slope, this is the slope function, so the y values here are all going to be 70. That means my slope is 70 the whole time, right? Okay, showing the relationship. And we're going to show, the whole point of this is to show, well, why is the area equal to the displacement? You're going to say, oh, that's easy. If I take the area of that rectangle, the area of that rectangle is 420, and it's equal to the displacement 420 if I did it on the row graph. Right? So you're telling the story incrementally coming up. And again, if I was doing it, I'm doing it right now. If I was doing it, I would take this and start adding details and then actually write it the right way, just to make sure I have everything right. Now, if you could do it without that, that's fine. That's kind of how I'd approach it. So it's a little sloppy, but we got that. So we have Riemann limit, FDC2 introduced. This would be a geometric model. So this is a nice geometric model of a simple example. Then what did we do next? We actually, okay, so now let's talk about it. Now, okay, all we've done here is we've talked about how do you find the area under a curve using Riemann sums, and why does it make sense that the area here is the displacement, right? Okay, so this would be, now we're going to phase 2. Okay, so this is all phase 1. I don't know if that makes any sense. So phase 2 is going to be what do we do next? What do we do next? Not quite yet. We did one more thing. The question is, how do we find area? So this is going to be, how do we find area under a curve? And to find area under a curve, we can take.
Yeah, the
We can take integrals. Okay, let's see how I want to categorize this. I'm trying to think here for a second.
Well, don't you have to like show how those rectangles can like?
Should use different colors. This. Oh, okay. Forget. I know what I'm saying. Okay, one way to find the area under curve, I could have a line like that. And if I wanted to find the area under the curve, would I have to actually take a true integral, or could I do it just geometrically? Right. So we could just find the area under here using geometry. Now there was two cases we did geometry. We did, well actually three cases. Something linear, or we could do the circle. Circle is one of them. I'll make this category. So you could have that. You could have a circle. And when you have a circle, you would just find the area of the circle. So if you integrated 16 minus x squared. Yes,
All that's to 1/2.
It's square root of 16 minus x squared.
Because that just generates a parabola.
Yeah.
What did I just say?
You said 16.
Oh, square root. I'm sorry. I didn't know what you meant. So if we take that, we know that's going to be a circle. And therefore, we would just take the area based on, if I said 0 to 4, that would just be a quarter of a circle. So we could take the integral by geometry, the integral by geometry. Are there any other cases? I think those are the only two. Oh, absolute value. You could do absolute value, you had something like that. So you had absolute value of x. So these are the three main cases you could take an integral without doing the fundamental theorem of calculus number 2, right? Correct?
Absolute value.
So, in reality, have we done anything with fundamental theorem of calculus yet?
No.
Well,
We did intro, we did limit, we want to know the area under the curve equals displacement.
that's just
But that's not necessarily fundamental theorem of calculus number 2, is it?
That is. That's the.
No, the fundamental theorem of calculus number 2 says I take the antiderivative of the displacement of the antiderivative.
That's basically.
Can you repeat that again?
That's basically.
You just said? You take the antiderivative of the...
So I'm going to say, now I'm done with my, this is my buildup. And all this stuff's in your notes, so it should be pretty clear what we're doing, I think. We're saying, let's say that you're